Hello, David here, and welcome to Robot Reachability Part 2, where we continue to learn how to locate a robot in order to reach all of the required positions. This video is a continuation of the concepts introduced in our Robot Reachability Part 1 video, which we will link to in the video descriptions on both YouTube and the Visual Components Academy. So maybe check out Part 1 first before continuing with this Part 2. We begin in the Program tab, and in this layout we have a robot with a welding torch, a workpiece positioner, and an imported CAD model placed on the table of the positioner. We first want to check the robot joints, so selecting the robot using the jog tool, we check the jog panel on the right. We have a list of joints here, J1 to J6, along with EJ1 and EJ2 for the external axis of the workpiece positioner. And when you interact with the robot joints using the sliders for joints J1 to J6, you can see the joint values change. And by double-clicking with your mouse, you can select the joint value and input your own. Now we can check the joint limits of the robot. Joint J1 has a limit of -180 degrees to +180 degrees, which you can see if you place your mouse cursor over the slider control. And to test these values, you can move the slider to the maximum left and right positions. Now we will reset the simulation to set the robot joints to their default values, and demonstrate how it appears when joints are exceeding their joint limits by creating two robot motion statements. Before we begin, you should check from the jog panel on the right that the tool selection is set to the tool center point or TCP of the welding torch. We will first use the snap control to snap the TCP to a corner of the workpiece. Enable the bisector snap type from the TCP snap panel on the right if you find it difficult to snap to the position. Then from the program editor on the left, we will add a point-to-point or PTP motion statement for that location. And then we will snap the TCP to the other side of the workpiece and add a linear motion statement. The maximum speed of the TCP in Cartesian space applied to the linear motion is too fast for this example. So in the Statement Properties panel on the right, we can double left click on the max speed value and change it to a value of 100. And we will do the same for the PTP motion by editing the joint speed to 50%. We can then reset and run the simulation and use the jog panel on the right to monitor the joint values. And you can see that almost halfway through the motion, joint J3 begins to move outside of its limit and is now highlighted red. And if you place your cursor over the joint J3 in the jog panel, you can see that its limits are from -120 degrees to +150 degrees, and currently it is greater than 150 degrees. To solve this problem, from the limits section above, we can enable stop at limits. And if we then reset and run the simulation again, once the simulation hits the limit, the robot motion will stop, and the joint will again be highlighted in red. And best practice in this scenario is to first reset the simulation. And whenever you have stop at limits enabled, you should also enable message panel output. And if we press play again, the simulation will stop. And in the output panel below, we receive a message that joint J3 has exceeded its value of 150 degrees. Now that we have checked the robot joint limits and how we can monitor them throughout the simulation, we will now take a look at the various robot arm configurations. We can delete the motion statements we added in the program editor on the left and create a PTP motion statement and see what arm configurations are available for the robot. We will use the Snap tool again to snap the TCP to this position on the workpiece. And if we check the arm configuration of the robot in the jog panel, the current configuration property is set to front above no flip. However, we want to save this position with the front above flipped configuration, where joint 4 is flipped. So from the program editor on the left, we create a PTP motion statement for this position. And with a PTP motion statement, the arm configuration we choose, for example front above flipped, along with the joint turns, is saved. And if we then select the robot and reset the simulation and check the jog panel, the default configuration will again be set to front above no flip. And returning to the PTP motion statement we saved, the configuration is, as expected, set to front above flipped. Basically, these robot arm configurations allow you to reach a point in different ways. And if we refer to the PTP motion statement again, it retains the front above flipped configuration. And if we then return it to front above no flip, you can see that the TCP is still at the same location, but using a different configuration. And a point worth mentioning is that robot configuration names are brand specific. This robot is the generic articulated robot by Visual Components, and the configuration names are as they appear in the jog panel. So let's go to the Home tab and browse the eCatalog for the Fanuc ArcMate 100IC. And then returning to the Program tab, select the robot, and checking the jog panel, we can see the configuration names are different. So configuration names are unique and brand specific. And another point to mention is that for a normal 6-axis robot, we expect to have 8 configurations, derived from front, back, up, below, flip and no flip. And now let's look at Robot Singularity. We will begin with a new layout, including the Visual Components generic articulated robot on a pedestal, and the welding torch tool has been replaced by a parametric suction cup gripper, which we modified, reducing its size to a 3x3 configuration before attaching it using the PNP tool in the Home tab. We also have a conveyor and a box that we will use later. And as we did in our previous layout, we modified the location of the TCP by selecting the robot and from the jog panel set the gripper TCP as our tool. Our first example will be wrist singularity, which occurs when joints J4, J5 and J6 are in line, with joint J5 in the 0 position. We can either manipulate the joint directly using the jog tool or modify the joint value from the jog panel on the right. And notice how within this configuration we can rotate joints J4 or J6 and the TCP will be in the same position. And when discussing robot singularity, we should note that it occurs only in robots that have at least 6 axes. So for 5-axis or delta robots, singularity does not occur. And also, the default configuration of many of the 6-axis articulated robots you will find in the Visual Components eCatalog are in the singularity mode. So let's drag and drop the Fanuc ArcMate 100IC from the eCatalog again, and returning to the Program tab, selecting the robot using the jog tool, we can see from the jog panel on the right that this Fanuc robot also has 6 axes and is by default in the singularity mode, since joints J4, 5 and 6 are in line, with joint J5 in the 0 position. And now let's try and simulate wrist singularity and see how the simulation deals with it. Let's first reset the simulation so that the joints are in their default positions, and from the limits section above, we will enable the limit for singularity. We could also stop the robot motion when singularity occurs by enabling stop at limits, but we will leave it unchecked for now. And we also want to enable the message panel output option, so any error messages appear in the output panel below. Selecting, for example, the parent coordinates option from the jog panel, or you could select object, whichever works best for you. Let's drag the TCP to the left using the green Y-axis arrow. What we want to create is a position where joint J5 is no longer at 0. Then in the program editor on the left, create a PTP motion statement. And to slow down the motion, making it easier to examine the movement of the robot joints, let's use the Statement Properties panel on the right and set the joint speed of the PTP motion to 10%. Now, while we are including a PTP motion in this example, we should point out that singularity is more common when using linear motion statements. And using the Y-axis arrow again, drag the TCP in the opposite direction to a position where joints J4, J5 and J6 are not in line, and create the linear motion statement and set the max speed to 100 mm per second. As we noted in our Part 1 video, from the 3D World toolbar on the left, enabling frame types and robot positions makes it easier to see the locations of your motion statements in the 3D world. If we select the motion statements we have created, the robot will jog to those positions. Wrist singularity would not occur at these positions, since joints J4, J5 and J6 are not in line, and there is just one set of joint values that supports these positions, except for any other configurations available for this robot. We're given the same positions of joints J4, J5 and J6, wrist singularity may also occur. So now we have the jog panel visible, we will reset and run the simulation to see if singularity occurs. The robot will first perform the PTP motion where singularity will not occur, and while performing the linear motion, when we reach the point where joint J5 is at 0, we will see the joints flip, and an exceeded singularity limit message will appear in the output panel below. Let's now right-click to clear the output panel, enable stop at limits above, and reset and run the simulation again. And if we check joint J5 from the jog panel, when the robot motion stops at the limit, joint J5 will be at 0. Singularity occurs when in certain robot configurations there are an infinite number of joint value combinations to place the TCP in the same position, and the robot cannot figure out which solution to choose, and the robot joints may accelerate to a point which is beyond the mechanism's capabilities. Robot programmers will often design their robot cells to avoid singularity, and some robots support automatic singularity avoidance. Another example of singularity is overhead or shoulder singularity, referred to in visual components as polar singularity, which occurs when the axis of joint 1 and the center point of the wrist joint are aligned. Since in this example we want to start a robot motion from an overhead position, we have moved our default configuration from here to here and applied it by either clicking play or save state from the simulation controls. So now when resetting the simulation, the robot will return to this position. And we remember to set the tool TCP like we did before. Then, as we did when examining wrist singularity, with parent coordinates selected we will drag the TCP to the left using the red x-axis arrow, creating a PTP motion statement and set the joint speed to 10%. And drag the TCP in the opposite direction, create a linear motion statement and set the max speed to 100 mm per second. Let's disable stop at limits above and reset and run the simulation while monitoring the joint values using the jog panel. And while the robot is performing the linear motion, when the point of singularity is reached, joint 1 will flip. And resetting the simulation to run it again, we can enable stop at limits, so the robot motion will stop once singularity occurs. Let's now take a look at an example of how to avoid singularity. First, we will return the robot to its previous default configuration and program the robot to reach down to grasp the box on the conveyor. So with our tool TCP selected, using the jog tool, we will drag the TCP down and snap it to the box. Then create a linear motion statement, edit the name to grasp, and set the max speed to 100. Then using the blue z-axis arrow, drag the TCP up, create a PTP motion statement, edit the name to approach, and set the joint speed to 10%. Then drag the approach PTP motion statement up above the grasp linear motion statement so the robot will perform the approach PTP motion first. Then let's reset and run the simulation. As the robot approaches the box, joints J4, J5 and J6 will become in line, and as joint J5 reaches 0, wrist singularity will occur. And since stop at limits is enabled, the motion will stop. There are a couple of solutions to this problem. One would be to move the robot back away from the box, to add an angle to joint J5 so it no longer reaches the 0 position. Let's right-click to clear the output panel below, reset the simulation, and using the jog tool, select the linear grasp motion statement. Of course, if we move the robot, we need to consider the position of any motion statements created for it. So first, from lock positions above, select to reference, which will lock any positions to the robot. And then using the move tool, select the robot and drag it back using the red x-axis arrow. Then returning to the jog tool, select the grasp linear motion and move the TCP back to snap it to the box, and use the touch-up control from the program editor on the left to update the position. And then selecting the approach PTP motion, using the move tool instead, drag the position back into place. And when using the move tool, you don't need to touch up their position. When adjusting positions, you will want to monitor your joint limits. Disable stop at limits if you want to allow the joints to go beyond their limits. Using the jog tool, you can use the jog panel to monitor the joints or watch for the origin ring at the center of the position turning red if you move the joints too far. And similarly, when using the move tool, if you move a position too far, the origin ring will turn red and the position name will turn yellow. Now let's reset the simulation and try this solution to see how singularity is avoided. We can also try moving the robot and leave the motion statements in place, and the robot will adjust its motion to reach them. So with the robot back on the pedestal, we set lock positions to world, which will lock the motion statements to their current position in the 3D world. And again, use the move tool to move the robot. The robot will move to reach the positions, and singularity is again avoided. And again, we can reset the simulation and check the results here too. And the third solution would be to lower the height of the robot. So leaving lock position set to world, selecting the move tool, use the blue Z-axis arrow to drag it down a little and reset and run the simulation again. And use the jog panel to check how far away from zero we have been able to move joint J5. And if we need to move it down a little more, repeat the process until we are happy with the updated position. Of course, in all examples, we would need to adjust the position or height of the pedestal. In this example, selecting the robot, we can copy its Z-axis value and then selecting the pedestal, paste the new height value into its component properties, and then resetting and running the simulation again with joints J4, 5 and 6 no longer in line, wrist singularity is avoided. In this next layout, we have the generic articulated robot again with the parametric suction cup gripper, which has been returned to its default configuration of 5x5, making it a little easier to see joint rotations. And our next topic is setting up the starting position for robot motions that include joint rotations so they do not go beyond their limits. Some joints have a domain so large they can have the same pose using multiple values called joint turns. In this example, joint J4 has a range of -300 to +300 degrees, and joint J6 has a range of -360 to +360 degrees. So joint J6 has a range of 2 full rotations. Here we have quickly modified the geometry and appearance of a tool and placed 2 instances side by side to illustrate the point. With the robot on the left, using the slider for joint 6 in the jog panel, we can position the joint at -360 degrees and drag the slider to rotate the joint all the way to +360 degrees, rotating -200 degrees from 0 using the robot on the left, or rotating +200 degrees from 0 using the robot on the right would create an opposite turn, whereas going +200 degrees from -360 degrees using the robot on the left would result in a turn of -160 degrees, which is a similar turn to +200 degrees from 0 for the robot on the right, or vice versa. -200 degrees from +360 degrees using the robot on the right would result in a +160 degree turn, which is a similar turn to -200 degrees from 0 for the robot on the left. In our first example, using linear motion statements, when we run the simulation, the gripper is moving around the edge of the box, rotating 90 degrees after each turn. And as it's spinning around, joint 6 goes over the limit of -360 degrees. You can only fix such joint issues using a PTP motion statement. So what we will do is reset the simulation and select the first linear motion statement and create a PTP motion statement at this position, and delete the linear motion statement and then run the simulation again. And as you can see, we are still rotating beyond the limit of -360 degrees. And to fix this problem, we select the PTP motion statement and use the increment joint value control on the right side of J6 in the jog panel to move the joint 1 full rotation in the positive direction, so that it starts from the positive side, and then use the touch up control to update the position, and then running the simulation again and slowed down a little, joint J6 unwinds before starting, so that it has more freedom to rotate while performing the linear move and rotate motions. And once completed, we end up at minus 197 degrees, the position we were at before we touched up the PTP motion statement. The next joint turn example is a pick and place motion that is often used when training users how to teach a robot, and where sometimes additional rotation of joint J6 is added that the user did not intend to add. Let's select this linear up statement and add a halt statement so the simulation stops at that point. Then reset and run the simulation, and checking the jog tool, joint J6 is at minus 29 degrees. When moving the TCP, you would, for example, select the jog tool, and with parent coordinates selected, using the green Z-axis arrow, drag the TCP to the required position, which should be a location closest to the previous point, in this example around plus 28 or 29 degrees. So then selecting the PTP transport statement and checking the jog panel, we can see it's at minus 330 degrees, which is the reason the joint is spinning. And to solve the issue, we increment joint J6 in this PTP transport statement back one full rotation in the positive direction, so it's now at plus 29 degrees, and touch up the statement. And now, deleting the halt statement, we can reset and run the simulation, and the unwanted joint rotation has been removed. In this final example layout, we are again performing a pick and place motion, but where the end position is out of reach of the robot. So from the robot positioners in the eCatalog, we add the visual components robot floor track and attach the robot to it using the PNP tool. And then in the Program tab, we set up our pick and place motion statements, and once the box has been grasped, we can use the axis of the robot floor track that appears in the jog panel to move the robot into position and create either a linear or PTP motion statement, and then add the remaining robot motion statements to place the box on the pallet. And this concludes the lesson. Thank you for watching.